Oh, thank you. Okay. All right, shall we get started? Some people are just coming in. All right. Oh, welcome to our first full day of our exploring, what did we call it? Highest energies, colliders at highest energies or something. And so we're going to start off this morning with most of our experimental talks. So our first talk today, this is an open conference to many ideas that are not just about muon colliders. Larry will be giving us a dedicated muon collider talk called How to Build a Muon Collider. Go ahead, Larry.
Yeah, we have to talk about muon colliders at some point this week. This is obviously gonna be kind of a high level overview thing, but it's not gonna be super comprehensive. I hope to tell you something that you haven't seen before and this kind of thing. So let's have some fun. So before talking about the far future, we all really like looking to the past for some insight and some perspective. And I do think this is a really important way to approach this problem. So I do want to take a second to talk about, of course, as you all know, one of the highest energy colliders ever proposed in the middle of nowhere, Texas. And you know exactly what I'm talking about. Yes, I'm talking about the late 19th century practice of smashing trains together. And this is a real thing that happened in the second half of the 19th century, where, if you can believe it, these were publicity stunts for the train companies, for the passenger rail companies, to try to get people to be excited about trains. And I guess it's exciting in some sense. And so what they would do is they would sell tickets for people to take the trains to the middle of nowhere, and then they would set up two trains and crash them together. And so, as you can imagine, this is an incredibly high energy. We'll get to that in a second. But so this is one of the most famous ones that ever happened, called the crash at Crush. Crush was a made-up fake town in the middle of nowhere. There was no town there; it was empty space. Indeed, in Texas, and actually not so far from the SSC site. And you know, this is less than an hour away, which on Texas scales is not very far, especially considering how big the SSC was to be. So yeah, this is in the middle of nowhere. I love this ad for this event that tried to sell tickets for this. It's a little hard to see maybe, but it's start at 4 p.m., finish at 4:01 p.m. because they were just going to smash it, and that's the whole thing. I really love this thing, and I'm interested in the fact that it was so money centric, right? It's $20,000 of a collision, right? And for some reason, they really wanted to think about it in that way. And I really love these little corner things. It's $20,000 crushed, $20,000 burned. And my favorite one is the last corner, which says $20,000 for science. It's a different time, maybe. So whatever that means, this is something that got a lot of people excited. This was a big pastime. We're talking about taking two locomotives, each at 35 tons, 45 miles an hour. Sorry for the American-centric unit, which led to something like 10 to the 13 TeV of energy. Of course, it's a very composite object at that point, and if you try to, energy per nucleon or whatever is obviously very small. This is very non-relativistic, let's say. But there's a lot of energy. And this was hugely popular, right? This particular one had 40,000 attendees. Only 2 people died. And there were, unfortunately, many injuries because there was an accident where something exploded that they didn't expect, whatever. But the crowds loved it nonetheless. So there were 40,000 people. Yes, exactly. And so The thing that's really interesting about this is that there were a lot of people that attended these things, and they happened all across North America. And one of the kind of main organizers of these things, not this one in particular, but events like this, he had the name Head On Joe Connolly. Just given that name because he liked to crash trains together. And at some point, somebody from the press asked Head On Joe why he thought that this was such a draw. Why 40,000 people would gather in the middle of nowhere, would travel hours to go see two trains get crashed together. And he said, I believe that somewhere in the makeup of every normal person, there lurks the suppressed desire to smash things up. And I think that's really a wonderful thing to think about. Now, of course, we're smashing things for rational scientific reasons, but there's this like underlying emotional thing that I think is not to be forgotten, especially when we're talking about recruiting new people, keeping people excited, keeping the public excited, which is, of course, as important as ever. So we're not interested in smashing trains, but we are interested in high energy collisions. So that's to say, let's talk about smashing stuff at 10 TeV. I'm not going to give the overall theory motivation for any of this because I want to talk about the actual building of stuff. But of course, we're interested in just in a minute, the 10 TeV scale for, and we're trying to be careful about this, we're talking about concrete physics targets, even if we sometimes do like to play in the realm of naturalist motivations. We are interested in concrete physics targets, and that's to say things like playing in the electroweak restoration limit, where your energies are much larger than your Higgs VEV, actually measuring the full shape of the Higgs potential, those WIMP dark matter targets, this kind of thing. So we want to reach this scale, and it turns out, I think as you all know and as you've all seen, muons are a great way to reach that scale. So it turns out you can get to super high energy because the fact that it's so much more massive than the electron means that you're not limited by synchrotron radiation as you would in E plus E minus. And of course, those mu's are not composite, although we can talk about the PDF, and that's kind of interesting. So those mu's are not composite. So that's to say the beam energy is translating into your hard scatter energy in a much more favorable way. And we're very lucky because our accelerator colleagues tell us that this might even be possible with a whole lot of work. And one of the important things that's going to come up a couple times in this talk is that the success in this program is really going to require that the HEP community really values and supports the accelerator community. And that really cannot be forgotten. I think that's something that, say, over the course of my professional career, had been lost, I think. And I think that's something we need to get back. And even maybe, on occasion, dip out of our lane and contribute where we might be helpful. So you've probably seen this before, this sketch, this conceptual design that exists for how to do a muon collider like this. This design is largely from the US MAP program from however long ago, with updates from the IMCC, but it's more or less taken this rough shape. This is, of course, from the article from Science last year, and a kind of more recent sketch from the IMCC is on the bottom here. So just to be to overly simplify this, what happens is you take a beam of protons at the kind of megawatt level, and you smash it against a target. You get a bunch of pions coming out of that, and you then allow them to decay to your muons, and you capture those muons. At that point, then you need to undergo this process of cooling this muon beam, which is only barely a beam at this point, to make it into something that is suitable for a collider, and then accelerate those muons, collide them, of course, and then measure what comes out. And we're going to talk about lots of elements along this chain. So the thing is, if you manage to make a muon beam, you of course have one fundamental problem, and that is that those beams will decay. There's nothing you can do about that, these muons will eventually decay. And of course, they have a lifetime of 2 microseconds. So step one, boost the hell out of them so that instead, if you're going at super high energy, you get that gamma factor of something like 50,000. So you're taking that microsecond lifetime and now talking about 100 milliseconds in the lab frame, which is much, much more manageable, although still very much a challenge because that number is way lower than the infinite lifetime of, let's say, more or less infinite lifetime of all the other things we like to collide. Good. So the problem is once you get these muons up to that 5 TeV scale so that they live long enough for you to do stuff with them, then that means their decay products are going to be now at the TeV scale. So now you have TeV level electrons that are going around and hitting your detector, your entire detector volume, whatever that might look like. We'll talk a lot more about that in a second. But also deposit lots of energy throughout the accelerator complex, which is yet another challenge. We're also ending up with TeV scale neutrinos at that point, which is then going to tell us that we need to carefully consider mitigation of that neutrino radiation, but flipped in the other direction, what can we do with that beam for getting physics out? So all of this is to say that no matter what you do with this whole chain of the kind of muon collider, whatever, the whole of the muon collider, every little bit of that has to be done very quickly, and every element needs to be heavily shielded and rad hard. And really, almost all of the challenges that come up are going to be due to the muon's short lifetime. Fundamentally, you can trace all these challenges back to that. So, like I said, this is overly simplified, in part because it's only a couple of words on here, but also because every single one of these things poses an enormous challenge. Right? This is not easy stuff. Each step along the way, we're talking about reaching space charge regimes in that proton driver that we've never seen before. We're talking about inventing a new way of doing targetry at this high of a power in this way, in a safe way, whatever it might be. A lot of magnets that are some of the most advanced magnets we've ever even thought of in rad-hard environments in some cases. We need to do this 10 to the minus 6 volume reduction in phase space for this cooling process. We need some of the biggest, strongest magnets. We're talking 40 Tesla magnets. This is a challenge all around, every single element of this, all the way through to the particle physics experiment that's going to be full of background that we need to mitigate as well. The rough plan right now is that we want to take this conceptual sketch, maybe not being fully fair to every element of this, some things are of course more advanced than others, but we want to take this conceptual design over the next, say, 5-year time scale and move to something more of a reference design, which is to say full simulations with end-to-end technical requirements. And this is the goal. I want to spend some time talking about this muon cooling stage because, in as much as I know about it, let's say, this is, of course, one of the most famous problems, although I hope I have demonstrated that there are a lot of problems besides this as well, a lot of challenges to overcome. But for this muon cooling, when you produce muons in this way with a proton driver, they have a huge phase space volume. Okay. And that's to say they have a large 6-dimensional emittance. But if we want to get to colliders that have a reasonable luminosity, so that we can get to those physics targets that we want, we need to reduce that 6D emittance. And you can see in that plot on the top, emittance goes down, lumi goes up, great. So we need to reduce that emittance. But if you think back to classical mechanics, if you have a volume in phase space and you want to reduce it, that requires a non-conservative process. So what we need to do is to remove energy from that system, hence the name cooling. And this is at least the way that I like to think about it. So we need to undergo some non-conservative process to cool this beam. So the stupidest, simplest sketch is that you might take some beam of muons with some spread in momentum, send it through a dipole, and end up with some non-zero dispersion. And the way that I like to think about this is that you end up correlating your momentum with your position. That then allows you to shove it through a wedge-shaped absorber such that those particles with a higher momentum traverse more of the absorber volume. That's to say, the higher momentum stuff loses more energy, loses more integrated DEDX. And the lower momentum stuff goes through less of the absorber. Right. So what happens is after the absorber, you end up with a beam that has a slightly smaller phase space volume. Okay. Maybe we're talking a 10% emittance reduction per cell. You then have a slightly lower energy, so you use some RF to restore that energy, and you just rinse and repeat. This is the simplest way of thinking about this. So if you just do this a lot, if you have order 100 cells, that 10% reduction done, order hundreds of times, gives you that necessary 10 to the minus 6 cooling. 10 to the minus 6, so a factor of 1,000,000 sounds really scary. The way I like to think about this is to then remind you that we're talking about a 10 to the minus 6, a factor of 1,000,000 on a phase space volume. That is to say a 6-dimensional volume. So it's much less scary sounding to say we're talking about a factor of 10 on average in each of those 6 dimensions. That sounds way more doable than factor million, right? So, great. The actual problem is that this rinse and repeat model is not so simple. Is that when we're going along this chain and doing this hundreds of times, we have to deal with losses at each step. And if you're losing the beam, then what's the point of cooling in the first place? And these late stage cells become incredibly hard to make because they end up requiring very high field magnets. We're talking, in some cases, a whole bunch of 14 Tesla sitting around, and in the final cooling, we're talking about very high field magnets. And all of this requires RF, or most of this requires RF to work in those fields. So this is really hard. And when we're talking about demonstrators, which I will in a second, the point is that we don't need a proof of concept to believe in ionization energy loss. That's fine. We understand how DEDX works. That's not a problem. What we actually need is a proof of engineering demonstration that we can actually build this kind of a magnet. We can build these magnets and put them next to each other, that we can build RF that operates in that we can send a beam through that safely. All of this stuff. This is what actually needs to be demonstrated, not ionization cooling. Okay. So we need to show that this can be physically constructed. And there are conceptual designs and kind of technical, let's say more than conceptual, designs for putting this kind of demonstrator where you're taking a bunch of cells and you're putting them together and operating them with a beam at Fermilab at a bunch of different possible locations, or at CERN, again, with a couple of potential options there. So this is part of the game now, and this will be a major goal of actually demonstrating this part of the chain at some point, let's say in the next decade or two, let's put it that way. I want to take a second to just a side note here. This ultra simplified view, note that if you have the opposite charge, this has the opposite effect. Right, that dipole is going to be sending your higher momentum stuff through less absorber. So that's a problem. So that ends up meaning that you need 2 parallel channels, one for mu plus and one for mu minus. And that's, let's say, expensive. And that seems really hard. So one of the things that some of us have been working on lately is to revive an old concept from the map era of this kind of peculiar design, which sends the particles in a helical shape, constructed in exactly the right way to allow for cooling of both signs of muons at exactly the same time through one channel. This won't work for the whole thing, but it can work for some portion of the thing. And if we can, for some portion of the thing, reduce 2 parallel channels into one, that could be a useful cost savings. So just to mostly to show fun animation, which, oh, right, no, I exported to PDF. Sorry, I'll put that up later. So the point is just that we end up sending these beams through this helical path in a way where the charge flipping, instead of adding a sign on the dispersion, ends up giving you essentially a phase shift, a longitudinal phase shift in the Larmor motion along this channel. It's a really interesting design. This could allow for an initial stage cooling that works on both at the same time, hopefully for some cost and kind of complexity benefit. Good. So I'm going to skip a bunch of steps now at this point and go all the way to the collider. There's a lot of interesting stuff in there, but that's why you need a whole week, say, at the beginning of this this workshop to go through every little bit of this. So thinking about the collider, thinking about the particle physics experiment that happens at the end of this chain, near the collision point, near the interaction point, we have lots of energy from these decaying muons, right? If I said earlier that we're talking about TeV level objects being thrown around. Turns out we have a lot of those TeV level objects being thrown around the experimental region. So much so that we're talking about an integrated EeV level energy incident into the detector region. So that's rough, and we have to deal with that. And these collectively will be called beam-induced backgrounds. We of course have beam-induced backgrounds at the LHC today, but I promise this is a different beast. This is not, just halo. It's not just upstream beam gas. It's not that kind of thing. It's instead EeV level energy being shoved into the detector region. So this ends up with enormous backgrounds for us. So to give you a sense for what this looks like, this was a slide shown in the first week by Anton. If you have a muon coming in, so in this case, the detector region's on the right side of this plot, or this figure. You have a muon coming in and decaying to that electron. That electron is now sitting in a magnetic field in the final focus and is going to be just thrown around by that field. In that process, it's going to emit a lot of photons. So much so that we're talking about 750 GeV worth of photons being just thrown into this environment. Yes, into the detector region, but also, just as importantly, into the final focus region, into just the magnets all around. And so you can see all of this gray here is all the shielding that you need to add to get an understanding, to be able to avoid this energy deposition giving you problems in your magnets. And then, of course, even by the time that the electron itself is entering into the, hitting a wall or whatever, that's still 450 GeV worth of energy. So this is a lot, but this is also going to be happening something like 10 million times per bunch crossing. So that's the actual problem here, is the scaling isn't on our side, right? That's how you end up with EeV level or whatever it might be. Good. So what can we do on the particle physics side? What can we do with the experiment? So first and foremost, we need to work very closely with the folks doing the accelerator design. And that's something, again, that comes up a whole bunch when you're playing in the muon collider environment, that it becomes, I mean, it was always crucial, but it becomes a new kind of crucial to play nice with the accelerator folks. And that's to say, especially in this machine detector interface, the MDI of this setup. So there are lots of things. Every little change to the accelerator lattice can have huge effects on the amount of background seen by the detector. And then the other thing that is kind of much more brute force is just put a big shield in the way. Right? So we really need to shield ourselves from this stuff. And so that's a huge part of what we do. So in this figure in the top, imagine that the collision point is happening in the lower right-hand corner. So you have the particles you want coming out of that collision point. But then you have something coming from the beam at some high angle maybe, coming and hitting this blue shielded region, and then hopefully coming to a stop. So that's great. So you have those, whatever it might be, hundreds of GeV to maybe even TeV level objects being stopped in a block of tungsten. that helps us reduce the bib by many orders of magnitude as seen in the detector itself. But the interactions with the shielding will end up bleeding all sorts of secondary energy into the actual detector volume. So that ends up being the main source of our background. But what this does is that it turns this highly localized, again, hundreds of GeV or TeV level electron showers or whatever, into a diffuse energy that's leaking into the detector. So that's great because that's changing, in addition to changing the overall normalization a bunch, it's also changing the character of the bib such that we have the ability to reject it through measurement, through careful measurement in the actual detector. So these cones here, these are the nozzle shields that we are always talking about. We put those in a way that really very much hurt our forward physics program. We're trying to figure out how to recover that program, but we think it's worth it to get rid of all of that background. And what happens is if you have one of those electrons coming and hitting that shield, you end up with some shower. That's some simulation of one of those electrons doing so. But again, now imagine 10 million of these, and you end up with a sizable background in your detector. So that's to say, this is not what my title slide should have looked like. It should have looked like something like this. Good. So by the time we're trying to build that detector, we need to deal with some very central challenges in the design of this. So one, we very much need to build a detector that is very robust to this bib, to whatever bib is leaking out of the nozzles. In the detector region, maybe I shouldn't say this so strongly, but there's a whole lot of MeV scale neutrals. There's other stuff around as well. But from the bib, that's kind of what's dominating. We're having neutrons and photons bouncing around and leaving all sorts of energy depositions around. Luckily, though, those neutrals and this background is not particularly in time with what you'd expect, and it's not particularly projective from the origin. It doesn't point back to the collision point. So to give you a sense on the timing side, while you of course expect, given some reasonable assumption of stuff going pretty close to the speed of light from the collision point, say you expect stuff to your signal to be at some particular value, your background is spread across a large range of times, in a kind of featureful way, right? The signal, the interactions from the bib are arriving both prompt and late, and I should actually say early in many cases, because when you have something coming off of the beam, you end up with modulo interactions with the nozzle, a shorter path length than stuff that has to go all the way to the origin and then back out. So that's to say that the time should be a useful handle for this. And in this 2D plot here, we're looking at the y-axis being the expected time of arrival, assuming beta of 1 from the origin, and the x-axis is the actual time of the hit or whatever. So you can see in red, this is the kind of stuff that we want to see from our collision products, and in the rest of the colors is your bib, as you can see, coming in early often, but also late. So that's to say we very much need timing resolution throughout much of the detector on the order of tens, maybe in some cases hundreds of picoseconds. So this is a kind of a new level of timing requirements built into all of our measurements that would be really important to get this physics out of this machine. Another important central challenge to this is that by the time we're talking about 10 TeV, yes, we're interested in getting a lot of VBF processes, which I'll talk about a little bit more at the very end, but only a little bit. But there's also a lot of interesting physics happening in the annihilation process, which is to say stuff that'll give us multi-TeV objects out. So we have to now deal with multi-TeV objects as the norm, as a norm in this machine. And that very high momentum tail for these objects is just going to be a lot more common, right? This is not cutting off into into a very steeply falling distribution. So we have to build these detectors in ways that can handle lots of objects with very high scale. Last week, Patrick told us he wants hadronic WZH discrimination at 5 TeV of a boost. If you think about that in terms of the normal rule of thumb, 2m over pt, that's an incredibly small angular separation between those boson decay products that we now have to deal with. So we're talking about needing incredible angular resolution, incredible segmentation, this kind of thing, to get out something that's a very central part of the physics program. So to just kind of say how much of a problem this might be and how much we need to be thinking about this. Of course, when we're talking about TeV objects being the norm, that means objects are living longer in the lab frame by a bunch, and just against the backdrop of the CMS pixels there, a 1 TeV B hadron, the average decay length in the lab frame is you're talking about something like 10 centimeters. So this is saying that today's exotic signatures or very rare signatures become really bread and butter. Or for that matter, if you have these super high energy showers, you need more interaction lengths in your calorimeter to stop those showers, right? Just things need to be scaled up in some way. Good. So this is a super challenging environment for particle physics. Let's actually try to build an experiment. So this is a picture of the Maya detector concept that many of us work on. There's, of course, want to say that there's also the conceptual design music that exists as well. I'm not going to really talk about that here. For the Maya side, there's a bunch of people, and probably this has grown since I first made the slide, so sorry for anybody who's left out there. And for this group of people, a lot of us kind of grew up on Atlas, even though many of us are now on CMS. So it's important to note that Maya is one of the many daughters of Atlas. So we kind of like that. Good. So this is more or less the shape of it. It looks like a particle physics experiment, a modern particle physics experiment, with the addition of these conical shields in the forward region. You might recognize this as being the thing that was on that cover of Science. Indeed, this is the renderings that we were making from our simulation exactly rendered for the cover of Science. In the first week, this was called an artistic interpretation. This is actually our simulation, so it's fun. And of course, that's the coolest thing I could ever imagine, making something on the cover of Science. So the overall idea for this, again, it's relatively simple, but there's some things to point out. So like I said, we want to scale up the detector. One thing that's hard to scale up is the magnet. And so that's to say, unlike previous muon collider detector concepts, this is more like Atlas in the sense that the solenoid is going to be before the calorimeters. We're talking about a 1.7 meter radius, 5 Tesla solenoid at the middle of this thing with something like a 1 Tesla return. This allows us to have a magnet that's a little more, maybe a little easier to make, although I'm not saying that would be easy to make, and allow us to build on top of that, outside of that, larger calorimeters if we need to. Again, for those increased number of interaction lengths. We put this before the ecal, which is then saying that we're going to be reducing our precision on our E gamma objects. But again, likely that means that this is easier to build and operate. But one nice extra thing is that then, put differently, this shields the ecal or the calorimeter systems from that bib quite a bit. And you can see that in this plot here, going from the blue from the previous design to the red where we're putting that solenoid inside, a great decrease in the amount of bib energy deposition in the ecal. So while it might hurt our signal performance somewhat, this helps reduce our background quite a bit. So just a few words on each of the systems here. For the tracker, we're talking about a system that gets something like 10 measurements on track in the barrel region, a vertex detector in the middle at the very center, which is a pixel-based system with a double layer for the very first layer. And then going further outwards, again, a traditional hunk of silicon that we use to measure this stuff. As we said before, we need to prioritize timing resolution here. And you can kind of see here, yeah, we're talking about 30 picosecond time resolution in the innermost detector here. That allows us to reduce the bib occupancy quite a bit. You can see on the right plot there, going from the blue to the greenish yellow or whatever, is a drop of about an order of magnitude in occupancy. And that's from placing now pretty strict requirements on the timing of the hits. So that's going to be super important. Once we apply that kind of timing requirement, we're talking about occupancy levels and readout levels and radiation levels not too dissimilar from HLLHC. So that's a nice target there, if we can have access to that level of timing information. We then, of course, use that tracking information for tracking. And in this case, we're using ACTS, a kind of experimental agnostic tracking software to do this. And despite the large population of bib, we're able to get to a nice reconstruction efficiency for these tracks and actually a pretty low fake rate, although I don't show it on here. But as you can imagine, adding that bib goes from left to right in this efficiency and does reduce our efficiency a little bit. This is first pass level stuff, and there's a lot of room for optimization here. Going further out a little bit, this is what a photon would look like in the ecal for Maya. And you can see it's swamped in all this bib interaction here. So it's a little bit hard, but if we look at this in a different way, in this case, this kind of XY projection, you can see the photon in the lower right. And that looks pretty different from the bib background. So we're lucky that that looks like that. If you look at that kind of shadow that exists around the ring, that is your bib contribution. But you can see it falls off pretty quickly with R, or with layer. So that's lucky. That means that we should be able to tell the difference, because we can certainly tell the difference looking by eye. So we just need to, that's to say we need to prioritize longitudinal segmentation in this calorimeter so that we can actually see that shower evolution and how distinct it is from the bib falling off quickly. Good. Our actual performance for looking at these kinds of photons is pretty good. We're talking about a photon RICO efficiency, despite this large background here, of something like greater than 95%, with energy resolutions that are at the percent level. So this is pretty good, especially given the going to the red curve on the bottom is with bib. Again, going further out into the hadronic calorimeter, this is roughly what a neutron would look like, as again said by simulation here. Again, kind of sitting in this background of all this noise from the bib. But given all that, we're still able to tell the difference and retain a pretty high efficiency of neutron reconstruction, again with let's say less than 10% level energy resolution, even at, well, at high energies, let's say. Okay, so that's the detector. I didn't talk about all of it, obviously, but just for the sake of time. We often look at plots like this, which is to say production cross sections as a function of square root s. This is fundamentally a detector slide, so I'll get there. The thing is, when we're looking at plots like this, it's important to remember what it would look like in the detector. So that's to say, let's add another axis here, which is to say, at a given instantaneous luminosity, what would actually be the event rate in the detector? So you can see here something like our VBF-Z production as at an order 10 to the 0 hertz, so 1 hertz. and maybe our VBF Higgs production is at a tenth of that, right? So 0.1 hertz. This is really important to think about in this way from the experimental point of view, because this colliders, so these Lumi numbers and all this other stuff are coming from an assumption that we have a 10-kilometer ring, which is to say an interaction rate of 30 kilohertz. So we often talk about in the muon collider world, like, we think we can run triggerless because this is a pretty low rate and all this other stuff. But it turns out our interesting physics is sitting more than 4 orders of magnitude below our collision rate. So that's to say, if you look at the muon smashers guide, an early paper on this that was kind of laying out physics targets like this, they defined a total cross section, just as a proxy for the total cross section, as VBF ZW, which is to say something like the Hertz scale. And so they made very nice statements that were really important in thinking about this, that something like 1 in 10 events has a Higgs, which is true if you normalize it that way. But it turns out that we're actually talking about 1 in 10 to the 5 collisions actually having a Higgs, which is a very different picture. So that's to say we're swamped by a whole bunch of uninteresting stuff. You can see some, well, okay, some of this is interesting, sorry, Jen. But a lot of this is like soft hadrons and this kind of thing we don't actually care about. So this brings into question, well, this tells us that we've been thinking about this a little bit wrong from the experimental side. And this will have huge implications for the detector design, for especially the readout of the detector, for whether or not you want to trigger and what that trigger might look like. And something that I think is interesting to point out is, so this is 4 orders of magnitude before you get to that Z, again, what this paper called the total cross section. Which is way more than the fraction that we throw away at the LHC or keep at the LHC. That's only a factor of 400 today, right? Instead of factor 10 to the 4. Also interesting, all of these scales that we're talking about for the muon collider side are all way less than any of these rates at the LHC, which also gives us an interesting game to play in terms of how much latency there is to think about this kind of thing. Good. So this is a relatively simple treatment so far, with full respect to everybody. It's relatively simple. These are conceptual designs, which is to say we really need detector level R&D that we'll hear about in a second to realize any of this performance. We have lots of room also on the super high level experimental side in the reconstruction algorithms that we're using. But we more or less believe that we would be able to do physics in this environment given such detector technologies. Overall, across the entire chain from that proton driver to the experiment, we don't see any serious problems with this that are going to make it impossible to do this whole thing. And we've really looked. But what we do find is a whole lot of significant challenges. Challenges that will really require a lot of hard work, a lot of smart people gathering together, just really a lot of elbow grease to make this thing work. Such a collider is decades away. We should not, lie about that. But the work starts today, right now, and that's to say that this will continue. And we touched upon this in the discussion a little bit yesterday with Jen's question. I think it's important to remember that humanity just wants to know what happens if you smash stuff together harder, right? Because we just don't know the answer, and as Chris said yesterday as well. And the only way to continue this far into the future is with muon colliders. And we gather to make that happen. Okay, thank you.
All right. So we have around 5 minutes or so for some questions for Larry. Does anyone want to start? Okay.
Thanks for this If I remember correctly, for the LHC, you're comparing the level 1 trigger
That's level one,
right?
yeah. Which is to say, thinking about electronics readout as the limitation. Yes.
Okay.
Yes.
I was naive, thinking the reason we need a trigger for the LHC is because whatever the data streaming, we know so much data, right? Here the event rate is much lower.
Exactly.
Even even at the collision rate, aren't we able to almost record all the data?
So I think it is probably true that we could build a system that could just read that out. The question is, what concessions do we start to make to do that? Put a different way, is there opportunity there? If we could be only writing out, let's say, order 10 hertz or something like that, something that sounds so slow, something like 10 hertz, do we have a whole lot of extra time to do something much more advanced on the detector, for example? Or do we have the ability to only read out a tiny fraction of the time and save on that power consumption? The transmission of the data is a large fraction of the power consumption, and the power consumption is a large driver for the amount of material in your tracker, let's say. So there's lots of interesting experimental questions here for what opportunities might there be? Yeah. 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 Absolutely. Absolutely. Yeah.
I'll just add to what Larry said, like the assumption that we could probably pull
Right.
that we're write out every channel with all of you could save that. There's no way you could read that out. It's just absolutely not going to happen.
At 30
So
kilohertz.
at 30 kilohertz. Right. So the question is kind of how do you balance per detail with not having a trigger or having a trigger, and where is the space in between them that you could explore? Other
Maybe it's not a question for you necessarily, but is there any physics that we would be missing if you only save it at I don't know, 10 hertz or 1 hertz?
We've been trying, as we built up this plot, we've been trying to understand what sits in this space here.
Right.
And indeed, like as we've been talking with Zhen and others about what you can do with the neutrino interactions from essentially the beam-induced neutrinos, the bins as they call it, interacting with your detector. Can you get interesting neutrino physics out of that from your main detector or from something that you build next to the main detector, this kind of thing? Yeah, that's a really interesting question. I struggle to understand what collision stuff would be all that interesting in terms of soft hadrons. Fine, you do one measurement or you do a heavily pre-scaled kind of measurement or something like that. But there just might be opportunity to throw away stuff.
It's not at all obvious that you can identify these rare things though easily before doing readout of your detector.
And I think as we were talking about before, this also points to the importance of let's make the kind of PDF treatment super mature so we can really understand all of this stuff and understand what physics opportunities we might be throwing away if we start throwing away events.
Just
yeah, I think it's fine. Yeah.
Should I just think of it as being sort of soft things emitted from the radiation? That's what you're talking about. You're not talking about beam crap getting in your detector. That's a different thing. That's not in this.
Yeah, exactly. So I think if you wanted to understand like a per readout element, beam-induced background, that's way up here, and that is awful. This stuff here, this is mu mutahadrons, but the vast majority of that cross section is going to be low enough energy. So I mentioned that, like for example, for Maya, we're talking about a 5 Tesla field. In order to get out of that tracker, you need to be it was 2.5 GeV or something like that. So all of that's going to be curlers if you're charged and just leaving noise in your detector, this kind of thing. But this here, this is a calculation for quote unquote jet, just to say high enough PT Q's and glues, and you know that starts to look like physics you might start to be interested in, and which is to say at a reasonable scale. So yeah, mapping this out, yes, is maybe an open question, and we really, I think this version of this plot, adding these gray things only happened yesterday. You know, so this is really hot off the presses.
This
Yeah.
has been a project while we've been here. And there's two, like, as Larry pointed out, there's two key things missing from here, which are the most common things. So there's no quantification of beam induced background, which we'd like to do with some like momentum cutoffs. And then there's also none of the incoherent E plus E minus scattering, which is what drives or can drive the occupancy in our innermost.
Yep.
So
Still waiting on a patch
trying
for the
to figure those
generator
out.
used for that. So, but yeah, this is ongoing, let's say.
Okay, I think it is time. We'll have more time for discussion later. So let's thank Larry